Aviation has long stood as one of humanity's most remarkable achievements, enabling global connectivity and economic growth. However, the industry is at a pivotal crossroads as the climate crisis demands urgent action. Aviation currently contributes approximately 2.5% of global CO2 emissions, with its warming impact amplified by non-CO2 effects such as contrails and nitrogen oxides. For an industry so vital to modern civilization, the question isn't whether to decarbonize, but how to do so effectively. Among various solutions proposed, hydrogen-powered aircraft have emerged as a transformative prospect capable of redefining the aviation landscape. Hydrogen is the universe's most abundant element, often lauded for its potential as a clean energy source. Unlike conventional jet fuels derived from hydrocarbons, hydrogen combustion produces water vapor instead of carbon dioxide. Furthermore, hydrogen can also be used in fuel cells to generate electricity, powering aircraft with zero harmful emissions. These attributes place hydrogen at the forefront of sustainable aviation technologies, poised to disrupt an industry seeking a balance between efficiency and environmental stewardship. To fully understand the transformative potential of hydrogen, it's important to explore the underlying science and mechanics of its application in aviation. Hydrogen can power aircraft in two primary ways: combustion engines and fuel cells. The combustion method involves burning hydrogen in modified turbines, mimicking the operation of traditional jet engines. This pathway is straightforward, but not without challenges. Hydrogen combustion generates water vapor, which, at cruising altitudes, can form contrails that trap heat and exacerbate global warming. Fuel cells, by contrast, offer a more sustainable solution. These devices convert hydrogen into electricity through an electrochemical reaction, emitting only water as a byproduct. While fuel cells are highly efficient and eliminate nitrogen oxide emissions, their relatively low power density compared to traditional jet engines limits their application to smaller aircraft or shorter routes. Nonetheless, continuous advancements in fuel cell technology are slowly closing this gap, promising broader adoption in the near future. Hydrogen's high energy density by weight is a critical advantage in aviation, where every kilogram saved can significantly improve payload and range. Hydrogen contains roughly 120 megajoules of energy per kilogram, about 3 times that of conventional jet fuel. However, this advantage comes with a caveat. Hydrogen has a very low energy density by volume, requiring it to be stored either as a high-pressure gas or a cryogenic liquid at -253 degrees Celsius. Both storage methods present design and engineering challenges, particularly for long-haul flights where space and weight are at a premium. Aircraft design is undergoing a revolution to accommodate these unique storage requirements. Leading the charge is Airbus, with its Zero initiative aimed at introducing hydrogen-powered commercial aircraft by 2035. Airbus has proposed 3 distinct designs: a turboprop for regional travel, a turbofan for medium-haul routes, and a blended wing body that reimagines aerodynamics and fuel storage efficiency. Each design incorporates cryogenic hydrogen tanks, requiring engineers to rethink everything from fuselage layout to thermal insulation. While the technical promise of hydrogen is captivating, its large-scale deployment hinges on the establishment of a robust and sustainable hydrogen supply chain. The vast majority of hydrogen produced today, over 95%, is gray hydrogen, derived from natural gas through steam methane reforming. This process emits significant quantities of CO2, undermining hydrogen's green credentials. The transition to green hydrogen, produced via water electrolysis powered by renewable energy, is both necessary and daunting. Electrolysis currently accounts for only a small fraction of global hydrogen production due to its high costs and energy requirements. Scaling green hydrogen production to meet aviation's demands will require unprecedented investments in renewable energy infrastructure. According to estimates from the International Energy Agency, IEA, decarbonizing aviation through hydrogen could necessitate over $1 trillion in investments by 2050. This figure includes the costs of developing hydrogen production facilities, constructing specialized storage and distribution networks, and retrofitting airports with hydrogen refueling capabilities. While these numbers are staggering, the long-term benefits of hydrogen-powered aviation justify the expenditure. Beyond environmental gains, hydrogen could stabilize fuel costs, which are among the most volatile expenses in the airline industry. The global hydrogen market is projected to grow from $150 billion in 2021 to over $600 billion by 2050, driven by increasing demand across sectors such as energy, transportation, and industry. Countries like Australia, Saudi Arabia, and Norway are positioning themselves as major exporters of green hydrogen, leveraging their renewable energy resources to produce and ship this critical fuel. Australia, for instance, has announced plans for the world's largest hydrogen project, a $36 billion initiative aiming to produce 3.5 million tons of green hydrogen annually by 2030. Pilot projects in hydrogen aviation are already demonstrating the technology's viability. In 2020, ZeroAvia successfully completed a test flight of a hydrogen-powered 19-seat aircraft, marking a significant milestone. The company aims to commercialize regional hydrogen flights by 2025, targeting routes under 500 nautical miles. Meanwhile, Universal Hydrogen is retrofitting existing aircraft with modular hydrogen capsules, enabling incremental adoption without the need for entirely new fleets. These initiatives, though small in scale, are providing invaluable insights into the operational, logistical, and regulatory challenges of hydrogen aviation. Beyond technical and economic considerations, hydrogen-powered aircraft have the potential to reshape the geopolitical dynamics of aviation. Unlike oil, which is concentrated in specific regions and often subject to geopolitical tensions, hydrogen can be produced anywhere with access to water and renewable energy. This decentralization could democratize fuel production, reducing reliance on traditional energy-exporting nations and empowering countries with abundant renewable resources. Regions like North Africa, with its vast solar potential, and Iceland, with its geothermal energy, could become significant players in the global hydrogen economy. Nevertheless, the path to hydrogen-powered aviation is fraught with obstacles. Safety is a paramount concern. Hydrogen is highly flammable, and its storage and handling require stringent protocols. Public perception of hydrogen safety, shaped by historical incidents like the Hindenburg disaster, remains a barrier to widespread acceptance. Overcoming these challenges will require not only technological innovation, but also transparent communication and robust regulatory frameworks. From an environmental perspective, hydrogen-powered aviation offers a compelling pathway to reducing aviation's climate impact. Unlike biofuels, which compete with agriculture for land and water resources, green hydrogen production through electrolysis has minimal environmental trade-offs when powered by renewables. Moreover, hydrogen can complement other sustainable aviation technologies such as synthetic fuels and electric propulsion, creating a diversified portfolio of solutions tailored to different flight lengths and aircraft sizes. Looking ahead to 2050, the successful integration of hydrogen into aviation could spur a wave of innovation across the sector. Advances in material science, such as lightweight composites and improved cryogenic insulation, will be critical for optimizing hydrogen storage and aircraft efficiency. Meanwhile, the development of hybrid systems that combine hydrogen with batteries or other renewable energy sources could provide flexible solutions for various use cases. In conclusion, hydrogen-powered aircraft represent a bold and necessary step toward a sustainable future for aviation. While the challenges are significant, the opportunities are transformative. By leveraging hydrogen's unique properties and addressing its limitations through innovation and investment, the aviation industry can achieve its decarbonization goals without sacrificing growth or connectivity. For those daring to imagine a cleaner, greener sky, hydrogen is not just a fuel, it is the foundation of a new era in aviation. The question is no longer whether hydrogen can reshape aviation, but how quickly and effectively it can rise to the challenge.